So this lecture is part two of our reactions involving Lewis acids. So we're going to move now into zinc, particularly zinc 2. Very interesting metal, does some great things with oxygen. And so we could use zinc chloride or zinc triflate. Triflate is oftentimes more soluble in organic solvents, which can be very helpful. And so what we're going to look at is a transformation where we take this like dibenzylic alcohol with some alkenes in a bridging chain, and we are going to do a reaction using zinc chloride with the loss of H2O. This is not a catalyzed transformation because the oxygen actually will, the alcohol will actually react with the zinc chloride, consuming it, and we don't have the ability to regenerate it unless we can actively remove water and maintain the integrity of the catalytic system. So we're going to form a tetrahydrofurion, a THF ring, looks like the THF solvent. It's fairly common with our AR groups and our alkenes present, and AR is just aryl, just some sort of aromatic ring. Could be a benzene. It could be a benzene with a methoxy group on it or something. It just kind of depends. So zinc chloride will react with, or zinc 2, excuse me, will react with the oxygen. It doesn't matter which one because of symmetry. So it reacts first with an OH group. Namely, it's an electrophile that engages the lone pair of electrons onto on the oxygen atom. And I'm going to pick I suppose I'll pick this, the right-hand oxygen to engage the zinc 2. So I'm going to write that as zinc 2 plus, just let it react to form a bond. And then we're going to get a zinc 8 species, which now has a positively charged oxygen atom. The oxygen can absorb the electron density from the carbon-oxygen bond to give rise to a carbocation that's stabilized by the aryl and the alkene. And what's going to happen is, if you're trying to jump ahead, my guess is you're not, but in case you are, the lone pair of electrons on the oxygen of the left side are going to now react with that positive charge on the right side to form the desired ring. All we have to do at this point is to lose hydrogen to give rise to our product. Long reaction, at least in terms of all of the writing we have to do. But I'm going to count this off, 2, 3, 4, 5, so that we can all see that it's indeed a 5-membered ring where the carbons on the oxygen have both an aryl group and a vinyl group. And all we have to do is lose hydrogen in this case to give rise to our product. Okay, so the zinc facilitated the loss of oxygen. And then once our oxygen was lost, and we could put a +1 in the zinc, it's probably countered by something. Once we lost the oxygen, we had a stable carbocation that could then cyclize using the neighboring oxygen to give rise to the final product. Note I didn't involve an O- at all because we're still technically under acidic conditions. We generate H+ in the final product. We have HCl everywhere in this reaction. There's no way we're forming an O-. It's the OH that adds and then loses hydrogen. Okay, now this is an important example because it illustrates that Lewis acids react with oxygen over CC carbon-carbon double bonds. And this is unusual because in many cases, strong acids often can react with alkenes. Most of the transition metals we looked at wouldn't care if there's an alkene present. They would seek out an oxygen atom. Titanium is another example of that. If we have alkenes present, even electron-rich alkenes, the titanium will still seek out the oxygen atom. And so if we had something like this, okay. And this is silicon with 3 methyl groups is TMS for trimethylsilyl, which is very common to use, but it's also the exact same abbreviation of another very common silicon-based reagent, and that's tetramethylsilane, the NMR reference standard, common for most deuterated chloroform experiments. So these two will react with each other in the presence of titanium 4 chloride, titanium tetrachloride. It depends who you talk to. And the product of this reaction is one in which the phenyl group, the carbon on the phenyl group, actually engages the thing with the trimethylsilyl functionality to form this as a product. And this is mediated by titanium and likely has some opportunity for catalysis with the right conditions, but the titanium likely is stuck and must be removed by workup. So this is another example where we don't have a catalyst, so not a catalyst. Okay, let's look at the mechanism of this transformation. The Lewis acid is going to react first. It's not zinc in this case, it's titanium, and I'm going to write titanium 4+. I mean, the ligands are fairly simple, just chlorine, so perhaps we could just use those, but it's fine. Okay. So what we're going to do is let our, this is actually called a chalcone, react with titanium 4+. The oxygen adds to the titanium to give rise to this species. There's probably still 3 chlorines attached. I don't know. It depends on what the solvent is. Okay. Now what we're doing in this case is we're actually adducting to titanium to activate the beta position. If we have carbonyl, then alpha, then beta. The beta position is typically a good electrophile. I should put a positive charge in the oxygen. We could consider a resonance structure to emphasize this point. It's going to put a positive charge at the beta position. And then this is going to react with our nucleophile. Now, our nucleophile is unusual. It has a silicon, but no actual charge. Turns out that silicon is basically a big proton and is very stabilizing towards positive charges, in particular what they call beta or neighboring positive charges. So what I can do is I can steal both electrons from here and add to this carbon. Now, due to the fact that we're using bond line structures, the product of this gets to be a little cumbersome to draw. Let me just use the starting structures as a guide, particularly on the easier part of this. So I've got my phenyl and everything. Now, instead of a positive charge at this carbon, I'm going to connect that by way of a new bond to the carbon that's going to, the carbon of our alkene. So it's going to be right there. Now that carbon had 2 methyl groups. So there's my 2 methyl groups. And over here is going to be a positive charge. Now that positive charge is on a carbon that has a positive charge is next to a carbon which has a silicon. So we say in this case is that, in just one second, I need to pause the recording for a minute. Sorry about that. We're back. Okay, so get the notes up in front of us again. So we formed a new bond and the positive charge is on a carbon next door to the silicon. The silicon provides extended hyperconjugation. because it's actually electropositive. So that carbon atom that is bonded to silicon actually is a little bit more electron rich, and the hyperconjugation effect is just a lot stronger when silicon is present. Now, additionally, silicon acts like a big proton. So what we can do is actually just simply lose it. We both stabilize the formation of that positive charge and then rapidly neutralize it through the loss of silicon. So silicon, being a big proton, it just sort of falls off, and that gives us this structure. Whoop. There we go. And then during workup, we can add a little bit of HCl. And the HCl will neutralize this enolate with the titanium. It's actually called a titanium enolate to give rise to this product. We showed the new bond. So, oh, there we go. Okay. Sorry about the phone call there. Okay. All right. And then we have our product. Goodness, just several phone calls on the last few minutes. Okay, so we have, we show the formation of our intermediate. I'm just going to emphasize here that the silicon or the silyl group stabilizes the carbocation, allowing us to, and this is called the beta silyl effect for what it's worth. But silicon is often used. It both increases the nucleophilicity of the pi bond and it stabilizes the resulting intermediate, and then it readily falls off. So it's a nice innocent bystander in all of this. And what happens to the silicon atom if you're worried? Well, I know you weren't worried, but it comes off as Si plus with 3 methyl groups. It's pretty stable. It's more stable than a tert-butyl group, a tert-butyl cation, and silicon being in the same group of the periodic table as carbon and tin means it's going to behave a lot like them. It can fit the various methyl groups around it. And so what we could do is we could next look at a tin reaction just to see if we can utilize all of those Lewis acids that we were interested in. And so here's an example where we take molecules get complicated. And we go here to here to CH3 to O, TMS, wedge to an H dash to an ethyl group. Okay, all right, big molecule or cumbersome molecule to draw, and then my notes say this is the product, and then something is crossed out. I can't tell if it's crossed out or if it's dashed. It looks like it's crossed out. Okay, that's all right. Okay, and that ethyl group stays the same, it turns out. Okay, so can we figure out what's going on here? First of all, I guess, how is this reaction occurring? It's using tin tetrachloride. So once again, we're not a catalyst because the catalyst would readily react with the oxygens and be consumed by the water product. Okay, let's look at what's happening in this transformation. First of all, we need to recognize that tin is a Lewis acid that's going to engage a nucleophilic oxygen. There's several oxygens to choose from. The one that gets us to a pathway towards some sort of thermodynamic endpoint, some sort of thermodynamic product, is the oxygen on the methyl ether. So we'll let this oxygen engage, and this is going to be tin 4. Oxygen engages tin 4 to give us this actually called stanated intermediate. because tin is SN. Okay, now we're at plus on the oxygen, 3 plus on the tin. And the neighboring oxygen wants to just bump that off. Don't want to forget my other groups here, O, TMS, and CH3. So the oxygen is actually going to bump this off. This is actually sort of a notorious reaction. I'm going to see if I can fit 2 structures down here. So ethyl. OTMS. And now we have this strange structure, and this is actually a structure that kind of pops up sometimes. It's very interesting in this application, but it can pose issues for the stability of some chemicals that have these, what are called methoxy methyl ethers. Okay, so anyway, this structure is now highly electrophilic at the carbon atom next door to that oxygen. That carbon atom can be shown as a positive charge. What I'm going to do instead, though, is to keep it as the better contributing resonance structure, but show that the neighboring pi bond can attack it and push the electrons onto the oxygen atom. The reason why it will do that is that the resulting carbocation, and first of all, we form a 6-membered ring, so the geometry is poised for that nucleophilic addition of the pi electrons from the carbon-carbon double bond. Now, the oxygen is neutralized, and we have this 6-membered ring. Well, while we have a stabilized positive charge, we have an opportunity to go somewhere else with it. What we could do is we could actually put the positive charge on the TMS group and let the electrons come down to form an oxygen-carbon double bond. But when I do that, I'm going to break the octet at this carbon. So what I need to do is figure out something that can sort of give. And actually, the best approach for us is to steal a bond from the 6-membered ring to make a 5-membered ring. So this is called a ring contraction because the ring gets smaller to a 5-membered ring. So let's draw this. We now have this structure. Here's our ethyl group now. Now, what happened to our silicon was our silicon fell away as a TMS trimethyl cation, but the electrons that came down to make down from the oxygen atom to push the carbon-carbon bond over made a double bond to the oxygen. So we now have a carbonyl, almost out of nowhere, it seems. Okay, this kind of is Grobe fragmentation-esque. Now, the way that things migrated, we observe stereoselectivity in, let's see, we have to observe stereoselectivity, right? Oh yeah, so the methyl group now is up and the carbonyl is down. So it's a little bit confusing because of the 2 methyl groups. So we have a CH3, this CH3 corresponds with this CH3, and then our other CH3 right here corresponds to the dash. So that's how we sort of flip our stereocenters around. This is another transformation promoted by a Lewis acid. It's a rearrangement, it involves a rearrangement after the loss of, in this case, a methoxy group to make a highly electrophilic carbon next door to the carbon oxygen, an electrophilic carbon that's double bonded to a positively charged oxygen. After forming a stable carbocation, we do a ring contraction to give rise to a 5-membered ring and neutralize everything but the TMS group, which is a very stable cation. The last thing I'll do is I will consider a Lewis acid that reacts with carbon-carbon double bonds. So an alkene Lewis acid that we could consider is X2. That is Cl2, Br2, I2, not really F2, and this is the dihalogenation And then there's a few variants on this, the halohydrin reaction, that sort of thing. But the dihalogenation of alkenes works pretty well. Okay, so what does this look like? Well, we could have our alkene react with X2 to give R, and then we could have X. And if we choose some, like if we choose one in particular, like bromine, we could go ahead and look at a mechanism of it. So one way to think about this mechanism is to first understand that what mechanisms do is they allow us to understand what intermediates are involved. So we use this halonium ion, and because it's bromine, we have a bromonium ion. And the way that may be formed, which is a little bit oversimplified, is we recognize that Br2 is just bromine attached to a good leaving group. So the pi electrons could add to that bromine atom and push off the good leaving group. But then we form an intermediate that doesn't form. We show the formation of an intermediate that doesn't actually form. We have a positive charge next to something with lone pairs. Those actually crash down, at least quicker than we can see. The transition state probably involves the simultaneous formation of both bonds, and maybe the picture of the bromonium ion is incomplete. But we don't actually add and then do a backwards add. It's just that the alkene approaches Br2 and forms the bromonium outright. But it's from the bromonium that we can start to push curly arrows that we're much more confident in. That is, we can have the Br minus engage, in this case, the more substituted position, because we're sort of under acidic conditions, allowing us to ring open from the more substituted position. Now, it doesn't matter that in this case, whether or not we add to the more or less substituted position in terms of the final product, because both of the X's are the same, so it doesn't matter which one added to the left or the right side. Okay, so this is our example where an alkene is the Lewis base, and the Lewis acid we needed in this case was X2. I could keep going with so many examples because there's so many Lewis acids out there, but I feel like I've probably even overstayed my welcome in terms of the material coverage on this. These are all very interesting transformations, though. But I think with that, we'll call it good for chapter 3 of Grossman. And then next week, we'll continue on with pericyclic reactions in chapter 4. So enjoy the lectures.